Good morning, sir. My name is Charanteja. I am from CSC IML, second semester. Today, my topic is X-ray crystallography, unveiling crystalline polyimide structures. This presentation explores the use of X-ray crystallography to analyze the intricate structure of crystalline polymerides, unveiling their unique properties and their role in advanced material designing. First, we'll talk about the introduction of X-ray crystallography. X-ray crystallography is a powerful technique used to determine the atomic and molecular structure of crystals by by shining X-ray onto a crystal and analyzing the pattern of different rays. Scientists can determine the arrangement of atoms within the crystal structure. This technique is particularly useful for substances like that from well-ordered crystalline structures such as main type of polymers including polymerides polymerides which are a class of synthetic polymer including materials like nylon are made up of repeating units linked by amide bonds. The ability to observe their crystalline structures can give insights into their physical properties such as strength, elasticity, and thermal stability. How X-ray crystallography works. X-ray crystallography begins with a few key steps. First one, crystal formation. To use X-ray crystallography, we first need a high quality crystal of the material in question. Crystals are essential materials in which atoms or molecules are arranged in a regular repeating pattern. For polymers like polymerides, the crystalline form is often more ordered, ordered than the amorphous form. In the case of polymerides, crystals form when the polymer chain are aligned in the organized fashion. These crystals can be formed in the laboratory through cooling or by allowing polymer chain to naturally arrange themselves. In the second one, X-ray diffraction. Once a high quality crystal is prepared, it is bombarded with X-rays. X-rays have wavelength on the order of the distance between atoms in a crystal. When the X-ray interact with the electrons in the crystals, they scatter in specific directions. This scattering produces a different pattern, that is, the X-ray are diffracted by the regular arrangement of atoms in the crystal, creating a 2D or 3D diffraction pattern. This pattern consists of spots known as diffraction peaks, whose position and intensities provide information about the arrangement of atoms in the crystals. Data collection. The different pattern is collected on a detector which captures the angle and intensity of the diffracted rays. This data is used to generate a series of equations that relate the diffraction angles to the position of atoms in crystals. Phase problem phase problem and electro density maps. One of the main challenges in X-ray crystallography is solving the phase problems, which refers to the fact that the different diffraction patterns only gives information about the intensity of a diffracted rays, not their phases. The phases are crucial for determining the extra positions of atoms in the crystal. Various mathematical techniques like Fourier transforms are used to solve these phase problems and reconstruct the electrodensity map, which shows where the atoms are located in the crystal. Polymerides and their crystallides. Polymerides like nylon 6,6 are characterized by the presence of amide linkage CONH in their structures, where this when these polymers crystallize, their molecular chain tend to align and pack in a regular manner, allowing for higher density packing of the polymer chain. Polymeride crystallization. Polymerides can crystallize in various ways depending on the conditions, example temperature, solvent and cooling rate. Some polymerides like nylon 6 can form a crystalline structure with distinct patterns, while others may remain mostly amorphous. Amorphous versus crystalline. In this crystalline region, the polymer chain are ordered and tightly packed in the amorphous regions, and polymer chains are distorted. The crystalline regions contribute to the strength and stability of the material, while the amorphous region may influence its flexibility. X-ray crystallography of polymerides. X-ray crystallography is especially useful for X-ray crystallography is especially useful for polymeride because it is directly reveal the packing and orientation of the polymer chain within the crystalline structures. Determining chain conformation. Polymeride chains can adopt various conformation depends on the presence of hydrogen bond between amide groups. X-ray crystallography allows us to determine the specific conformation of the polymeride chains in the crystal lattices. For instance, in the case of nylon 6,6, the polymer chain adopts a specific extended chain conformation where the chain are aligned in a regular straight fashion. This conformation is critical for the materials mechanical properties such as its tensile strength. Hydrogen bonding and intermolecular interaction. Polymerides exhibit strong hydrogen bonding between the amide groups along the polymer chain. These hydrogen bonding bonds play a crucial role in stabilizing the crystalline structure. By using X-ray crystallography, We can visualize the hydrogen bond between the amide groups and how this interaction contribute to the overall stability of the crystalline structures. This understanding is essential for designing polymeride materials with enhanced properties such as improved strength, heat resistance, or moisture retention. Crystalline morphology. X-ray crystalline morphology provides intense insight into the overall crystalline morphology of polymides. For example, it can reveal the alignment of polymer chain in the crystalline lattice, the size of crystalline domain, and how these domains are organized within the material. This information is important because the crystalline morphology influences the material's physical properties such as its melting point, hardness, and resistance to solvents. Application of X-ray crystallography in polymeride reaching research. The insights gained from X-ray crystallography have significant practical applications in the development and improvement of polymeride based materials. Polymer processing. Understanding the crystallization behavior of polymerides help improve processing techniques such as injection molding or extrusion, such as commonly used in the products of nylon fiber films and other polymeride based products. Material design. By investigating the crystalline structures of polymeride, scientists can design new materials with specific properties. For example, modifications to the polymer chain length, cross-linking, or chemical composition can be made to tailor the crystalline structure for desired properties like improving wear resistance, better thermal stability, or enhance mechanical strength. Polymer bending and composition. X-ray crystallography can also help in the study of polymeride blends or composites. By analyzing how polymerides interact with other materials such as glass fibers, or carbon nanotubes, scientists can create advanced materials with combined properties. Crystalline quality. Obtaining high quality large crystallines of polymerides can be difficult, especially for certain polymer forms that are inherently amorphous. Without high quality crystal, obtaining accurate data can be challenging. Coming to conclusion, X-ray crystallography is a powerful tool for unveiling the crystalline structures of polymerides, allowing scientists to to examine the arrangement of polymer chains, the role of hydrogen bonding, and the overall crystalline morphology. Thank you, sir.